So we are going to start chapter 3, which is on discrete random variables. So in this chapter, we are going to learn about random variables, probability distributions, measure of averages, or measure of averages like the mean, the average. We also speak about the mode, the median, as some measure of averages, and measure of variation, the probability distribution. So this is where we start dealing with converting most of real life issues into probability. We are also going to discuss about cumulative joint distribution and joint distribution. And 3.1, we will define random variables. So I'm going to send you the take-home problems today. They will be due on Wednesday, so that you look at the problems and then you know the difficulty you may have before we do the exam. So what is a random variable? A random variable is a function from a sample space to the set of real numbers. So x of s plus. The s is the sample space. So it consists of associating to an outcome of a sample space a real number. It is generally denoted by a capital letter and defined by its range. So, example, a die is rolled, let x be the number on the die. So when a die is rolled, it's a probability experiment. The outcomes are 1, 2, 3, 4, 5. So we are just doing like associate to outcome 1, 1, outcome 2, 2. That is a very simple example. We can also say that a die is rolled. Let y be 10 minus x, and x is the number of the die. Identify a random variable, and the value will be 10 minus 1, 9, 8, 7, 6, 5. We could say that a die is rolled if the number is odd, record it. If it is even, divide it by 2. There are many rules in associating to the outcome of a random experiment. You know, you can say you roll a die. If the number is odd, keep the number. Still with the same experiment, the die is rolled. X equals to x, so y equals to x if x is odd. X over 2 if x is even. X is the number on the die. So y will be what? Y will be 1, 3, 5. When you roll 2, you get 1. When you roll 4, you get 2. When you roll 6, you get 3. So this is the random variable. It is actually a function. We can say that 2 die are rolled. And we say let x be the sum of the two numbers. We could also say let x be the first number, let y be the second number, and let z be x plus y. So we have an experiment and we transform it into numbers. A coin is tossed. Let y be the number of heads. When you toss a coin twice, you can have head, tail, head, tail, head, tail. So here you have head, 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 tail, tail, head, tail, tail. These are the outcomes. If we count the number of heads, then we have 2 here, 1 here, 1 here. So random variable will be 0, 1. This is tossing a coin twice. We can toss a coin 3 times. We can toss a coin 100 times and count the number of heads. So far, we have been having finite outcomes. We can also have infinite outcomes. For example, you roll a die until you get the number 5. How many times are you going to roll the die? You roll a die until you get number 5. You can roll it first time and you get number 5. Second time you get. First time you don't get, second time you get. You can get it the third, the fourth, then we cannot tell how many times you will roll a die before you get number 5. So that is also an infinite random variable. We'll arrive at the bus stop at noon. The time t until the bus arrives is a continuous random variable. How long will he wait? Will he wait until the bus arrives? He can wait for 5 minutes. You can wait for 1/100 seconds. You can wait for. So the time until the bus arrives is a random variable, which is a continuous random variable. So a random variable can be divided into 2 types, discrete and continuous. Discrete random variables are those variables that with the range a discrete set. For those who did discrete math, you know what discrete sets are. For Daisha, you didn't do discrete math. We call a set discrete when you can count the elements of the set. For example, this is a discrete set. Even though it goes to infinity, we don't know how many, but it is discrete. Every finite set is discrete. It's not a very important element, but we just want to distinguish between random variables that are discrete and random variables. Maybe we should write that, because this chapter is about discrete random variables. I will just type it here. The random variable is called discrete. If it is a countable set, that is, you may count the number of elements in the random variable. So it is finite if it is a finite set. A discrete random variable is finite. A discrete random variable is finite if it is a finite set. We cannot say otherwise it is continuous. That's what I say in statistics class. But a random variable is not either continuous or discrete. But most of the time it might be continuous. There are mixed distributions. There is distribution that is discrete at a point or at a certain level and then becomes continuous later. We are going to look into that. So when we define a random variable, we may want to consider associating to that random variable a probability, because it was the result of a probability experiment. So we call it a probability distribution. A probability distribution is a function that assigns to each value of the random variable a probability. The function that assigns to each value of the random variable a probability. You can say that let x be a random variable p of x, example 1, is a, we can call it discrete probability distribution. Actually, I don't need to call it discrete, but I mentioned the word discrete here because I am going to express it as if it is discrete. It is discrete, and we call it discrete. And we call it a probability distribution. Whenever you hear probability distribution, it's the term used for this type of function on a discrete random variable. So it has this, the first property that I have here, for those of you who are used to functions, that is what I have here. So the domain is x, the random variable, and the range is the closed interval 0, 1. That is what we mean by p of x is greater than or equals to 0 and less than or equals to 1. Then the next condition is that the sum of the probability is 1. If the sum of the probability example, the die is rolled, let x be the number of die on the die. then the random variable x is 1, 6. This is x, p of x. Now, what is the probability of getting 1 when we roll a die? 1 over 6. 2, 1 over 6. This type of random variable with a probability distribution that is the same for each outcome is called a uniform distribution. This is an example of uniform. This is an example of uniform distribution. So this example here on the PowerPoint. The second example is a coin is tossed twice. Construct a probability distribution for the number of heads. Construct a probability distribution for the number of heads. So if a coin is tossed twice, the sample space will be head, 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 tail, tail, head, tail, tail. What is the random variable associated with this sample space if we are counting the number of heads? Yes. 0, 1, 2. Do you understand this, Daisha? Do you know where the numbers are coming from? The number of heads when you toss a coin twice. You can either have 0 head, 1, or 2. And we can make a frequency distribution theory. So for 0 is 1 over 4. For 1 is 1 over 2. We can see that if you add this number, you get. Sometimes you may be given a probability, a distribution, and you are asked to determine if it is a probability distribution or not as a function. Sometimes a distribution could be given as a function. And you might want to know, is it a probability distribution? Let's look at this other example. A box contains 6 blue balls and 7 red balls. 5 balls are randomly selected. Let Y be the number of red balls. Let Y be the number of red balls. What is the probability distribution of Y? This example, Y equals to 0, 1, 2, 3, 4, 5. This will be too much. I will reduce it to 3. So I will change it to 3 balls are randomly selected. Otherwise, we will do a lot of computation. Three balls are randomly selected. What is the probability that we will get? 0 red balls. Remember that how many balls do we have together in the box? How many balls do we have? How many in total? 16. Yes. 13. 13, right? So there is a full stop here. It's good for me to write 3 in letters. So we have 13 balls, and how many do we want to select? How many are we selecting? How many balls are randomly selected? We will randomly select 3 balls. So we have 13, combination 3. This is 13 factorial. You can use your calculator. So this becomes 13 times 2 times 11. 26 times 11. 286. So n of s is 286. Now remember that the probability of E is number of outcome in E divided by number of outcome in S. So we are going to use it to find the probability that we will have 0, 1, 2, or 3. And X be number of red balls. If X is the number of red balls, the probability that X equal to 0 is the number of ways to choose 0 balls divided by 186. So if no ball is red, then the 3 balls are what? If we select 3 balls and none is red, what does that mean? The 3 are what color? All 3 are blue. So we are going to select, there are 6 blue balls, 6 combination 3, divided by 13 combination 3. This is the general formula. If you have a calculator, you can use it in practice. The 6 combination 3 is 6 factorial over 3 factorial times 3. 6, 5, 4, 3 factorial. Which is 3 factorial is 6, and this is 20 over 286. divided by 2 is 10 over 1. So I can start the table here. 0, 1, 2, x, p of x, 10 over 1.3. Now we are going to do p of x equals to 1 will be the number of ways of choosing one red ball out of how many reds? How many balls are red? 7. So we want to choose 2 blue and 1 red. So 2 blue will be 6 combination 2 times 7 divided by 13 combination 2. 6 combination 2 is 6 factorial over 2 factorial times 4 factorial. So here is y, because I was using the random variable y. It doesn't really matter. You know what we have. I could even use red. So probability that y is equal to 1 is 6 factorial over 2 factorial times 4 factorial. That's 6 times 5 times 4 factorial over 2 factorial over factorial. Times 7. Let's go. 3 for 2 factorial divided 6 divided by 2 factorial. 7 divided by 4. This is 35 times 3. So the probability that y equals to 2 will be we have 3. 0, 1, 2, 3. The probability that y equals to 2 is that we want 2 red balls, so we will choose 1 blue. That's 6, 7 combination 2. Over 286. 6 times 7, 6, 7 factorial over 2 factorial times 5 factorial. 6 times 7, 6, 5 factorial over 2 factorial. So the 5 factorial simplified. So we are left with 6 times 21 divided by 286. So 1 of 6. That is 21 times 6. At this point, we can find the last one by adding this and subtract it from 286. But we are not sure if we didn't make any arithmetic mistake. So we are going to just do for y equals to 3. Probability that y equals to 3 will be 3 red ball. So no ball is blue. It's 7 combination 3 over 13 combination 3. 7 factorial over 3 factorial times 4 factorial. 7 factorial. You can write 7 factorial again as 7 times 6 times 5 times 4. This will go. 3 factorial is 6. So this will go. So we have 35 over 286. So let's check if we did not make a mistake. We want to do 2 plus 105 is 115. Let's add 35 to it. We have 0, 5, then 126. Pardon? Oh yeah, it was 143. So we are going to add the 10. That works, right? Thank you. So we have to check that way using the definition of probability distribution. If we define our probability distribution this way, it will always be a probability distribution satisfying the condition. But if I just say, I have a distribution, and I want to check if it is a probability distribution. Suppose I do this in step 101. I give them a number like this, minus 1, minus 2, 0, 1, and then I put 0.1, 0.4, 0.3, 0.4. Is this a probability distribution and why? Is this a probability distribution? Do you see anything wrong with this as a probability distribution? Anthony? Anything wrong with this as a probability distribution? It adds to more than one. A probability distribution is a probability. So it must be between 0, a sum. So what if I put here 0.5, 0.6, then I put 0.5, 0.3, minus 0.6. What about this? Will it be a probability distribution? One, the probability must be positive. Probability must be positive. This is just for you not to an easy type of thing, but sometimes you might be embarrassed not knowing how to determine if a given distribution is a probability distribution. So if a guy is ruled this, what we have done here, we will later on, when we will be doing example of discrete distribution, we will call this a geometric distribution, a hypergeometric distribution. It's a hypergeometric distribution. So let's look at this one, which is a negative binomial distribution. I want us to get used to those distributions as simple as what we can do before we give them the actual names. We have seen the uniform distribution, hypergeometric distribution, which is just an actual example of combinatorial probability. And let's look at this. A die is rolled until the number 5 is shown. Let Z be the number of rolls. What is the probability distribution of Z? What is the probability distribution of Z? Observe that Z will be equal to 1, 2, 3, 4, and so on. What is the probability that Z equals to 1? Take a little bit. What will be the probability that Z equals to 1? I want you to take a minute and think about it. What is the experiment? A die is rolled until you get number 5. What is the probability that Z is the number of rolls? So when Z equals to 1, it means what? 1 roll, you get 5. If you roll a die, what's the probability that you get 5? Daisha, what do you think? You roll a die. How many outcomes do you have? 6. What is the probability that the outcome is 5? 1/6. That is it, right? So we have 1/6. Probability that Z equals to 2. Remember, you are rolling until you get a. You are rolling until you get number 5. What is the probability that is at the second roll that you get number 5? It means the first roll you get what? A number which is not 5. And the second roll, what do you get? A number which is 5. What is the probability that on the first roll you don't get 5? 5/6. And 1/6 because they are independent, right? They are independent. That's what is helping us here. So what about probability that Z is equal to 3? That means first roll, no 5. 5/6. Second roll, what do we get? We will get 5 only at the third roll. First roll, 5/6. What should be second roll? If the first roll you don't get 5, what is the probability that you don't get 5 on the second roll? If you don't get a 5 on the first roll, what is the probability that you will not get a 5 on the second roll? Still 5/6, right? Because they are independent. If you roll a die, that when you are rolling the second time, it is still the same as if you did not do anything the first time. And now the third one, what is the probability that the third one will be a 5? 1/6. So having this, can we generalize it? The probability that Z equals to X will be what? All the rolls before the Xth roll we will put it as 5/6 raised to power x times 1. So this is the general probability distribution of this random variable. I'm sorry, not x here. I'm sorry. What should I write? X minus 1. X minus 1. I could define this again as the number of rows before you roll with 5. How many failure before you get 5? Then we will change it into, here we will start with 0. That distribution will be 0. How many failure before you get 5? If you got 5 the first time, then it is 0. No failure, first time you got. And we have shifted the distribution, and we'll be speaking about 0, 1, 2, 3. And it will also go to infinity, but in that case, we will put x here. So, I think we have learned enough for today. If you are ready with your problems, I will get it. I will send you the